In today's lesson, you will be learning how to implement sequential control using programmable logic controllers. So, what do we mean by implementing sequential control? Well, in certain processes or applications, there is a fixed operating sequence of motion. Hence, we will be teaching you a technique on how to solve such question easily. For a start, let's take a look at this example over here, whereby there is a bending workstation, okay, as shown in figure 1. And let's take a look at the operating sequence of this bending workstation. So you can see that in this bending workstation, there are two cylinders here, and this is the metal strip. So the purpose of this bending workstation is to bend this metal strip into a L shape. Okay, so let's read the sequence of motions over here. When the metal strip is located in the bending tool and the start push button switch is pressed, cylinder A will extend to clamp the strip. You can see that this is cylinder A and it will extend to clamp this strip. When cylinder A is fully extended, cylinder B will then extend to bend the strip. So you can see this is cylinder B and it will then extend to bend this strip. When cylinder B reaches its fully extended position, okay, it will then retract. So when cylinder B is fully extended, it will then retract back, okay. And finally, cylinder A will also retract and release the metal strip, which can then be removed by hand. Okay, so this is how this bending workstation works. And as you can read, in this example over here, it follows a fixed operating sequence, okay. So we will be teaching you how to solve such applications or such processes. And first, before we touch on the programming part, I would like to teach you how to express such sequence of motion in displacement state diagram and also abbreviated notation. Okay, so there are two ways of representing sequence of motion. One is displacement state diagram, another is abbreviated notation, or sometimes we call motion sequence. So let's proceed. Okay, so the first step now is to see how we can represent the sequence of motion using displacement state diagram. Okay, and I will draw it over here. So before we start drawing on the displacement state diagram, I would like to check the initial positions of the cylinder. I can see that cylinder A is retracted, okay, as shown in the diagram, and cylinder B is also retracted. And we represent 0 with retraction and 1 with extension. Okay, so let's first mark the initial positions of the cylinder on the displacement state diagram. Since both cylinders are retracted, I'll mark a 0 over here. Okay, so now let's proceed to read the question. When the metal strip is located in the bending tool and the start push button switch is pressed, cylinder A will extend. So now cylinder A is going to extend in this step. And in this particular step, cylinder B still stays retracted. So I will draw cylinder B staying retracted. When cylinder A is fully extended, cylinder B will extend to bend the strip. So in the next step, what happened is cylinder B will extend to bend the strip. Okay, and cylinder A in this step will stays extended. Next, when cylinder B reaches its fully extended position, it will then retract. So the next step is cylinder B will now retract. Okay, and again in this particular step, cylinder A is still extended. Okay, so it stays at its original position now, which is extension. Finally, cylinder A will also retract and release the metal strip. So the last step is cylinder A will now retract to release the metal strip. And in this particular step, cylinder B still stays retracted. So with this, we have completed the drawing for displacement step diagram. So what have you learned? if you notice, when I'm drawing the displacement step diagram, I always draw simultaneously for both cylinders. So in a particular step, I will draw cylinder A and cylinder B together, okay? I will not finish the displacement step diagram for cylinder A, then I will continue to do cylinder B, okay? So it's very important when you do displacement step diagram that you do it simultaneously in each step for both cylinders, okay? So this is how you draw the displacement step diagram. Next, we will take a look at how we are going to draw abbreviated notation, or as I told you earlier, it is also sometimes called the motion sequence. So now let's read the question and we shall start drawing. So when the metal strip is located at the bending tool and the start push button is pressed, cylinder A will extend, okay? So first I will draw some boxes over here. Okay, so the very first step is you have to press the start button, and then what happens is cylinder A will extend. So when cylinder A extends, we call it A plus. Okay. Next, how do you know that the cylinder is fully extended? Well, take a look at the pneumatic drive circuit over here. We know that when cylinder A is fully extended, it will touch 2LS. So when cylinder A extends and it touches 2LS, okay, then let's read the next step. Cylinder B will extend to bend the strip. So let's write this down here. Cylinder B will extend to bend the strip. Okay, and again, how do you know cylinder B is fully extended? Again, look at the pneumatic drive circuit. When cylinder B is fully extended, it will touch 4LS. So let me write down over here 4LS. Okay, and let's read the question again. When cylinder B reaches its fully extended position, it will then retract, okay? So cylinder B will now retract. And how do you know that cylinder B is fully retracted? Well, again, look at the pneumatic drive circuit. When it's fully retracted, it will touch 3LS. So let's indicate this down, 3LS. And let's read the last statement here. Cylinder A will also retract and release the metal strip. Okay, so the last action that's going to happen is cylinder A retracts, okay, and it releases the metal strip. And how do you know cylinder A is fully retracted? Well, take a look at the pneumatic drive circuit again. It will touch 1LS. Okay, so this is what we call the abbreviated notation or the motion sequence diagram. Okay, one important thing is you must always bring the last condition to the first condition. Okay, so I will also write over here plus 1LS. In other words, I'm checking that the cylinder is initially retracted first before it can extend. So what have we learned over here for the abbreviated notation? First, you will realize that I draw all the actions in the boxes, okay, like A plus, B plus, B minus, A minus are the actions of the cylinder, so they're all in the boxes. And other things, or the input elements, I all put it outside the boxes over here because they are the conditions for the action to take place. Okay, so to recap, I will also put the last condition, okay, to the first step, okay, over here as you can see. So whatever is at the last condition, I will always put it to the front as well, so as to ensure that it starts off where it should be. okay, for the cylinder positions. So you can see from this abbreviated notation, when you press the start button and when the cylinder is at initially retracted position, cylinder A will extend. Okay, when it's fully extended at 2ls, cylinder B will then extend. After that, when cylinder B is fully extended, it will then retract. Once it is fully retracted, it will touch 3ls and cylinder A will retract as well to release the metal strip. And how do you know that it's at fully retracted position? It will touch 1ls. Okay, this is a single cycle operating sequence, hence I draw it this way with no looping. Okay, so this is for the abbreviated notation, or we sometimes call the motion sequence diagram. So you can see in figure 4, this is how we wire up the PLC diagram. Okay, so you can see that in this diagram, this is the PLC controller where we wire the input elements to the input card and the final control output elements to the output card. Okay, so now let's go on to this page over here where we will talk about the principle of the shift register technique, okay, which is the technique we are going to use to implement sequential control. In this diagram over here, we are trying to illustrate to you how the shift register technique works. So let me walk you through this diagram now. And this diagram was drawn with reference to the earlier example, which is the bending workstation. So what happened is, when you first press the start button, cylinder A will extend. Okay, so when cylinder A extends, it will clamp the metal strip, and when it is fully extended as detected by the 2ls, B will then extend to bend the metal strip. So when B is fully extended and it touches 4ls, B will then retract. When it is fully retracted, 3ls will be activated and A will then retract to release the metal strip. So how do we know that A is fully retracted? It will touch 1ls. So this is how this process works, and you can see that there are actually 4 steps, okay, to complete this entire bending workstation process. So in each process, okay, or in each step, I call them group, okay, group 0, group 1, group 2, group 3. Basically, they are just names, okay, to represent each step. So in step number 0, or I call it group 0, okay, what happened is cylinder A will extend. In step number 1, which I call it group 1, B will extend. In step number 2, which I call it group 2, B will retract. And in step number 3, which I call it group 3, A will retract. Okay, you may ask, why do I call it step 0 instead of step 1? Okay, well, because in programming, okay, we always start from 0. Okay, that's why we call it group 0, group 1, group 2, group 3, instead of group 1, group 2, group 3, group 4. Okay, so the reason why we name it this way is for programming purposes later on. So just take it as this is step 0, step 1, step 2, step 3, which we are calling it group 0, group 1, group 2, group 3. Now, let me take a look at these functions over here and see how I can relate them to this diagram. So one of the functions of the shift register is it provides memory. So what do we mean by memory? Okay, memory means that we turn on one group at a time, okay, which in programming we call it latching. Okay, what happened is, like for instance in group 0, which is step 0, okay, A will extend, and only in this step A will extend. So only when this step is completed, okay, then it will go to the next step. So in order for this step to keep turning on, okay, or stays at this step, we need to provide memory, which I will illustrate to you later on in ladder diagram what we meant. Okay, now let's take a look at this set. Okay, For instance, let's take a look at this step over here, or this group 1 over here. For this group 1 to take place, first, group 0 must first take place, and it has touched 2ls, okay, it is fully extended. Then group 1 will take place. So what are the conditions for group 1 to take place? First, this step must happen, which is the previous step, and cylinder must be fully extended, okay, according to the bending workstation process. So set means the start conditions to prepare for this group to happen. So what do we mean by reset? Okay, so you can see that once this step happens, I need to turn off the previous step, okay, which we call it the reset, okay. How can we off the previous group, or how can we reset the previous group? So all this we will be touching on later on in the next example on how we can draw ladder diagram to achieve sequential control. So now let's take a look at array first before we go through the example. I would like to now explain to you what is an array and how can we apply them in the shift register technique. So array is a kind of data structure that can store a fixed size sequential collection of elements of the same type. Okay, what do you mean by data structure? Okay, earlier in PLC chapter 2, you learned a few data types. Okay, data types like Boolean, which we use extensively in the PLC ladder programming. Boolean basically means true or false, or in our context, we always like to call it on or off, okay? We also learn about integer data types, okay, which we don't really use it for now. And there are other data types like real numbers, okay, time, okay, and so on and so forth. So I will not go and touch on that for now. Instead, I would like to focus on what exactly is an array and why do we use an array. Okay, so as you can see from the previous example, in each step over here, okay, I call them GP0, GP1, GP2, GP3, okay, so we are actually declaring them like individual groups, okay, so instead of declaring individual groups such as GP0, GP1, GP2, GP3, we are creating one array variable called GP, and inside they have 4 elements, okay, and they will be called GP0, GP1, GP2, GP3. So in terms of declaration in the PLC ladder diagram, let me show you this. Okay, so in the PLC ladder diagram, instead of creating 4 individual groups, okay, so this one is Boolean. Okay, instead of creating 4 times, okay, I'm going to create only 1, okay, and I call them GP. And inside this group, there are 4 elements in it, okay? So you just need to type Boolean with square bracket 4, which means that I am going to create GP0, GP1, and GP2, and GP3. So basically, if I give you an analogy, instead of having individual human beings, I'm having a family, okay, and in this family there are 4 members. Okay, so this is just an analogy to help you to understand. So you can see that in terms of declaring variable, array is very easy to declare, okay, just one statement, I already declare 4 members belonging to this family instead of having 4 individual names. Okay, and of course there are other advantages as well, which I will show you later on in the subsequent chapters. Okay, there's a key reason why we use array, okay, in doing this sequential control, which we will highlight to you in PLC chapter 4. So for array, you can see that in this example, okay, I created a family of GP, okay, inside there are 4 members in it, okay, and they are of Boolean type. Okay, so if I draw it out in this diagram over here, basically you can see that there are 4 elements here, okay, GP0, GP1, GP2, GP3, and inside it is either on or off, or I call it 0 or 1, okay, whether is it true or false, okay. So this is the data structure of this group. So now let's go through the example over here, which I'm going to illustrate to you how to implement sequential control with what we have learned so far. Okay. I'm now going to go through how to implement sequential control using the shift register technique. So you can see over here, we are using the bending workstation motion sequence diagram, which is also called abbreviated notation. So in the very first step, what happened is cylinder A will extend to clamp the metal strip. Then cylinder B will then extend to bend the metal strip. In the third step, cylinder B will then retract, and finally cylinder A will retract to release the metal strip. So this is the bending process, okay, which involves 4 steps. So you can see that we have actually created control relays, software control relays, okay, to achieve each step. For instance, in step number 1, which is going to be controlled by GP0, it will make A extend. And in step number 2, which is going to be controlled by GP1 software relay, B will extend, and so on and so forth. So in the very first step, I will create 4 software relays, okay? So I call the first one GP0, okay, square bracket. You can choose to write the name inside the coil or outside of the coil. So I'll write it outside of the coil because of my handwriting. So I will go on to achieve drawing all these groups. Okay, why? The purpose of creating GP0 is to make cylinder A extend. Okay, in fact, I can write the purpose over here. The purpose of creating this is to make A extend. The purpose of creating group 1 is to make B extend. The purpose of creating group 2 is to make B retract, and the purpose of creating group 3 is to make A retract. Okay, we always create software relay for a purpose. So I already write down what's the purpose of creating them. And if you notice, why do I put a square bracket? Okay, like GP0. Why do I have a square bracket that encompasses the 0? Well, because remember earlier on I teach you array. Because over here, I'm going to declare, okay, in the PLC program, the family of GP, which is used to control this sequential control, and it is of Boolean type with 4 elements inside. Okay, why 4? 0, 1, 2, 3 is actually 4. Why do we start from 0? Well, this is programming. Programming is always start from 0. Okay. So this is how we create the groupings. And why do we need to have array? Well, it's because of something that we are going to teach you later on in PLC chapter 4 under emergency stop. So for now, you just need to remember that we create an array of a family called GP, and the purpose is to achieve sequential control. And over here, we have 4 elements in it because there are only 4 steps to achieve this bending process. Okay, and in each step we are using a particular GP. For instance, I'm using GP0 to make A extend, followed by I'm using GP1 to make B extend, okay, GP2 to make B retract, and GP3 to make A retract. Okay, now I'll go to the next step. Step 2, provide memory to each group. What do we mean by providing memory to each group? Well, it means that when GP0 turns on, it should stay on, okay, and until something happens. So how do we make it stay on, okay, forever until something happens? Well, you have learned this before. All we need to do is to just create a latch. So let me show you this example over here. I'm going to create a latch, okay. Of course, the latch must be the same name as the coil, which is GP0, so that when GP0 turns on, the contact will also turn on, and GP0 will stay on forever until something here break the circuit, okay, which we are going through to the various steps later on. So let's focus on what we should do for this step 2, which is providing memory to each group. So let's go on and do for the rest of the group, which is to introduce latching. Okay, now I have drawn latching for each group. Next step, step number 3, we will be incorporating normally close contact to reset the previous group. Okay, so what do we mean by that? Well, let me give you an analogy. So we have this track and field relay race, okay, whereby there are 4 family members here: GP0, GP1, GP2, and GP3. Okay, 4 family members. So they are going to run this track and field relay race, okay, in this anti-clockwise manner. So GP0 will run, okay, or I should say that will turn on and run until it reaches GP1, then it will stop. And then GP1 will continue on this relay race until it reaches GP2, pass the baton to him, and then he will stop. Then GP2 will continue on this relay race and pass the baton to GP3. GP2 will then stop, and GP3 will continue on, okay? And this cycle just keep going on and on, okay? Depending on whether is it a continuous cycle or a single cycle motion sequence. So how am I going to integrate this into my ladder diagram? Well, the question says incorporate the normally close contact to reset the previous group. So same like the bending workstation, when the first step happens, okay, and when it has completed its first step, it will go to the second step, and the first step must be off, okay, that's what it meant, reset the previous group. So this is just like a relay race as well. When GP0 is on and running towards GP1, okay, when it reaches GP1, it will stop and GP1 will then continue. So when will GP0 turn off? Well, it will turn off when GP1 is on, okay? When GP1 is on, it will turn off. Because just like a relay race, there can only be one runner running on the track and field. The rest will just stop there and wait. So let me draw this here. When will GP0 stop? Okay, if you recall earlier, we have learned in PLC ladder diagram, okay, this is the latch, okay, things above the latch, okay, or within the latch, we call it the start condition, and things outside of the latch, we call it the stop condition. So we want to turn off GP0, so we will fill in here. So when will GP0 turn off? Well, when GP1 is energized. And when I draw normally close, it will become open and GP0 will turn off. Okay, now let's take a look at GP1. So when will GP1 turn off? Well, GP1 will turn off when it has reached GP2. So I'll write here GP2. So when GP1 reach GP2, okay, normally close of GP2 will become open because GP2 is now on, and GP1 will stop. Okay, do the same for the rest of the group. And perhaps I want to explain this for GP3. So when will GP3 stop? Well, GP3 will stop when it has reached the position of GP0. Okay, so we have now incorporated the normally closed contact to reset the previous group. Okay, which is actually reflected here as well. Now we'll take a look at the next step, which is incorporate the normally open contact to prime the next group. Okay, which means that what is the condition to start the group? So let's take a look at this first group here, GP0. Okay, so when will GP0 turn on? Well, GP0 will turn on, okay, as you can see in this analogy here, GP0 will run when GP3 pass baton to him. So as I have reminded you earlier on in PLC ladder diagram, this is the latch, okay. Things above the latch is the condition to start this control relay. Things outside the latch, which is this GP1, is the condition to turn off GP0. Okay, so now we are talking about the start conditions for the group. So one of the conditions for GP0 to start is GP3 passing baton to it. Okay, so now I'll draw this. So GP3 is the start condition. Okay, so things within the latch is the start condition, as I've told you just now. So GP3 is the start condition for GP0. Okay, let's take a look at the next one, GP1. So when will GP1 turn on? GP1 will turn on when GP0 pass the baton to GP1. So I will say that GP0 is the start condition for GP1. So you can go on and do for the rest, where who will turn on GP2? Only when GP1 pass the baton to GP2. So GP1 is the start condition for GP2. And lastly, when will GP3 turn on? Well, GP3 will turn on when GP2 pass the baton to GP3. So GP2 over here is the start condition. So now we have incorporated the normally open contacts to prime the next group, okay, which is the start conditions for the groups. We will go on to step 5. We shall now take a look at step 5, where we will incorporate other start conditions for the group, okay. So in other words, let's take a look at group 0 now. So you can see that group 0 is this, okay, where it controls a extension. And when will group 0 turns on? Well, group 0 will turns on when, okay, let me zoom this. Group 0 will turn on, okay, when the start button has been pressed and when the limit switch is activated. Okay, so you can see that these two are the other two conditions for this cylinder to extend, okay, whereby this cylinder extension is being controlled by group 0. Okay, I shall shrink this down a bit. Okay, so what are the conditions? Well, first is the start button, S-T-A-R-T, and second is the limit switch. Remember, we are drawing PLC here, so in PLC we either draw normally open or normally closed contact. So I will draw normally open because when it's activated, it will become closed and GP0 will turn on. So there are 3 conditions, okay, for GP0 to turn on. First, you must press the start button. Second, limit switch must be activated. And lastly, group 3 must be on. Okay, now let's take a look at group 1. So for group 1, you can take a look at the motion sequence diagram here. For group 1 to turn on, first, it must also activate 2LS. So only when 2LS is activated, group 1 will then turn on. So the conditions to start group 1, okay, is also 2LS. So let me draw here. So when 2LS is activated, normally open will become closed, and provided GP0 is on, group 1 will then turn on. Okay, so now we will focus on filling in the blanks. So you can see for group 2, okay, what is the condition to start it? Well, 4LS. Look at the arrow before it, which is 4LS. Okay, and how about group 3? The arrow before it will be 3LS. Okay, so we have now incorporated the start conditions, okay, like for instance in the first line we'll incorporate the start push button, okay, and the limit switch to trigger the group, and we also fill in the blanks for the other groups as well. Now let's take a look at step 6, where we will incorporate the output produced by each group. Okay, so take a look at group 0. Okay, what's the purpose of group 0? The purpose of group 0, as indicated in this motion sequence diagram here, is to make A extend. Okay, so again, I will just draw this here first. I'll write the comments, and the purpose of group 1 is to make B extend, okay, as I can see over here in the motion sequence diagram. And the purpose of group 2 is to make B retract. Group 3 is to make A retract. Okay, so now we are going to draw the output produced by each group. So to make cylinder extend retract, we need to look at the solenoid. Okay, so for our easy viewing here, I have actually copy and paste, okay, the cylinder positions, which you can find in your earlier pages. Okay, because I'm still using the bending workstation as the example, you can actually look at the bending workstation pneumatic drive circuit, which I am pasting it right here so that we can easily look at it, okay, and write down what we are supposed to do. Okay, so you can see that group 0 is to make cylinder A extend. So this is cylinder A. How do I make cylinder A extend? Well, I have to energize the first solenoid. So I will draw this here, 1 SOL, okay, and group 0 will make solenoid 1 extend, okay, or turn on, which means that A will extend. Let's continue to draw this. Group 1 is supposed to make B extend. Looking at cylinder B over here at the pneumatic drive circuit, how do I make B extend? Well, all I need to do is to energize the 3 SOL. Okay, so I'll write this here, GP1, okay, we'll energize the 3 SOL to make B extend. Okay, next, let's look at GP2. GP2 is to make B retract. How do I make B retract? Well, you can see that 4 SOL will make B retract because when the directional control valve is at this position, okay, let me draw here. The directional control valve is at this position now, okay. Cylinder B is retracting, so this directional control valve at this position is closest to 4 SOL. So 4 SOL, okay, will make B retract, and who will make B retract is actually group 2. Okay, so let me write this down here. And finally, okay, to make A retract, okay, I just need to energize GP3. Looking at this pneumatic drive circuit over here, to make A retract, all I need to do is to energize 2 SOL. So let me draw here, 2 SOL, okay, is to make A retract, and who will make A retract is actually GP3. Okay, so now we have actually completed this, incorporating the output produced by each group, and as you can see over here, the purpose of each group is just to achieve the outcome set out in each step. So for instance, in group 0, which is the first step, okay, I want to make A extend. So GP0 will make A extend. How does it make A extend? It will just energize the solenoid when it turns on. Okay, the same concept goes on for the rest of the groups over here. So with this, let's go to the last two steps, which is step 7 and step 8. We will take a look at step 7, which is to incorporate a cold start push button to boot up the operation. Well, let's take a look at this ladder diagram here, which I'm going to zoom in now. Okay, let's take a look at GP0. In order for GP0 to turn on, we have 3 start conditions here. Okay, 3 conditions that need to be activated. Then GP0 will turn on. Okay, the 3 conditions are start PB, cylinder at retracted position, and GP3 must be on. Okay, so the cylinder initially is at retracted position, and if you press start, GP0 will still not turn on because GP3 must be on. Okay, initially the bending process or the bending workstation, everything is at rest, meaning that all the groups are off, okay, because none of the steps are being activated, okay. The cylinder positions are all retracted, okay, nothing is moving. So in order for GP3 to turn on, I need to incorporate something called a cold start push button. Okay, if I give you an analogy related to what I told you earlier, which is the relay race, it's just that in a relay race, which is similar to this, the umpire or the referee will definitely ask the runners to get ready first. So now we are going to try and incorporate a cold start push button to get ready the system, okay, or we call it technically to boot up the operation. So let me draw this cold start push button switch at group 3. Why group 3? Because I need group 3 to turn on, or else group 0 will never be on. So let me draw this cold start PB. Okay, so when cold start PB is activated, okay, GP3 will be on, okay, and the contact here will close. Okay, so GP0 will not be activated yet. It will only be activated when the umpire, if I relate that to the analogy again, fire the gun and start the race. So in this case, it will be the start push button being pressed, cylinder at retracted position, and because GP3 has been on previously already by my cold start PB, GP0 will then be activated and cylinder A will extend to start this bending process. That is why you need this cold start PB to boot up the operation first. So to operate this bending workstation, the first thing you need to do is to press the cold start PB, okay, to ask it to get ready. Then you press the start button, then the whole process will start. So eventually, you will have this ladder diagram, which is step 8. This is the final ladder diagram for this bending workstation. So with this, we will go through more examples, and you will need to actually have some practices in order to familiarize with this sequential control using the shift register technique. Let's go to the examples now. We will now take a look at case study 1, where in figure 5A and B, it shows the pneumatic control circuit, okay, and the displacement step diagram. So the question asks us to write the motion sequence in abbreviated notation form, indicating clearly the limit switch for initiating each cylinder action. Okay, so this is part A of this case study 1. In part B, they said that the sequence of operations is to be controlled by a PLC. We have to design a program in ladder to achieve the desired control based on the shift register, incorporating the following fringe conditions. Okay, so the shift register is the technique that we have learned earlier. Okay, and we have to incorporate such that cold start PB will boot up the operation. okay, which means that it will ask the shift register to get ready, and the start PB is used to initiate the single cycle operation, which means that when you press the start PB, the operation will start, provided that you have already pressed your cold PB initially to boot up the operation. So let's take a look at this diagram over here. This is the displacement step diagram. So we are supposed to write the motion sequence diagram based on this. So let's take a look at the next page. Okay, before I go on to the next page, this is the PLC wiring diagram, whereby this is the PLC and these are the input elements, and this is the final control elements or output elements that can be wired to the output card of the PLC. So let's go to the next page. In order for us to draw this motion sequence in abbreviated notation easily, I'm going to copy and paste the pneumatic drive circuit and the displacement step diagram from the previous page over to this page, so that we do not need to keep scrolling up and down the pages. So I'm going to paste it over here. Okay, to begin writing this motion sequence diagram, first I will draw some lines. Okay, and I know that the question already mentioned, or the case study already mentioned, that to start this cycle, I need to press the start PB. Okay, so when we press the start PB, what happens? Well, let's take a look at the displacement step diagram. In the very first step, we can see that A will extend, okay? A will extend, while B stays retracted. So the only action that will happen is A extend. So let me write here, A plus. And how do you know that the cylinder is fully extended? Well, take a look at the pneumatic drive circuit for cylinder A. When cylinder A extends, it will touch LS2. So let me indicate over here, LS2. Now let's take a look at the second step. So in the second step, we can see that A will stay extended, so no action from A. However, B will extends. So let's write here, B extends. And how do we know B is fully extended? Well, take a look at the pneumatic drive circuit for cylinder B. We can see that when B is fully extended, it will touch LS4. Okay, and let's take a look at the third step. So in this third step, what happened is A will retract, okay, as you can see over here, but B will stay extended. So the only action we will see is A retract. And how do you know A is fully retracted? Again, look at the pneumatic drive circuit for cylinder A. It will touch LS1. And lastly, take a look at the fourth step, okay, whereby you will see that cylinder A stays retracted while cylinder B will retract, okay. So the action that we will see is cylinder B will retract. So how do you know that the cylinder B is fully retracted? Again, look at the pneumatic drive circuit. When it's fully retracted, it will touch LS3. And remember what I taught you earlier, the last condition, okay, must always move to the front, okay. So I will write over here to remind you, I'll write in red, I'll write plus LS3. So there are two conditions to start this cylinder A extension in this motion sequence diagram. First, you need to press the start button and make sure that cylinder B is at retracted position, which is LS3. So this is the motion sequence in abbreviated notation for this displacement step diagram. Okay, so I would also like to highlight to you that I would like to draw, okay, I will label in black now. I would like to draw the relays on this motion sequence diagram. Okay, what do I mean by that? Well, first I will label this as GP, 0, like what we have done previously in our previous bending workstation example. So in order for A to extend, GP0 must be on. So I'm creating groups, okay, which is the relay control, so that I can draw my PLC ladder diagram later on easily. And for the second step, I will call this group GP1. Okay, GP is just a name. Okay, just to recap what we have taught you earlier. So when GP1 is being energized, when GP1 relay is on, software relay is on, B will extend. And I will continue to label sequentially GP2 and GP3. So with this, I've already completed the motion sequence diagram. You can see that in this motion sequence diagram in abbreviated notation, what happened is all the input elements are always outside these boxes. I call them boxes, okay? So you can see all these are input elements, and the actions always stays inside the box itself. Okay, so that's why you can see I only write A plus B plus A minus B minus inside within the box. Okay. You will also realize I did not write call PB in the motion sequence diagram because call PB is just to prime the operation or just to boot up the sequence. It's not the button, okay, which is like start PB, which starts the entire motion sequence. So now I will take a look at the PLC ladder diagram and I will teach you how to fill in the blanks. In order to fill in the blanks for this PLC ladder diagram, I will first paste what I have drawn earlier, which is the motion sequence diagram, onto this page. And again, the purpose is so that I do not need to keep scrolling up and down. So this was the motion sequence diagram I wrote earlier, and I'm going to paste it here so that we can all refer to it to see how am I going to fill in the PLC program using this motion sequence diagram I've written in part A. So you can see that in this ladder diagram, we already create the groupings GP0, 1, 2, 3, and we even draw the template for you. It's just that we need to fill in the blanks for all this. So you are expected to know how to draw the template for this shift register technique, okay? So if you forgot how to draw, please refer back to the video, okay? And look at how I actually teach you to draw this shift register technique, okay, step by step in the earlier parts of the video. So now let's focus on what we're going to do, which is to fill in the blanks. Okay, you can see that GP0 is created because I want to make A extend. So I always like to write comments beside my ladder diagram so that I know why I created this relay, okay, this software relay. So the purpose of creating GP0 is to make A extend. The purpose of creating GP1 is to make B extend. And the purpose of creating GP2 is to make A retract. And finally, the purpose of creating GP3 is to make B retract. Okay, so now let's focus to fill in the blanks. So we can see that in order for A to extend, some conditions must be fulfilled. Okay, so we look at the arrow before it, which is this condition. The person must press start PB and LS3 must be activated. So let's write over here, start PB and LS3. Why do I write over here? Well, because you can see that this is GP0, okay, which is to make A extend. And all the start conditions, I will write it above the latch, or I call it within the latch, okay. So you can see that the condition is start PB and LS3. So when you press start PB, it will be closed, and when LS3 is activated, it will also be closed. So you can see that when GP3 is on, okay, which is activated by the cold start PB, GP0 will be on. Okay, now let's take a look at the next one, which is GP1. So for GP1 to turn on, okay, we look at the arrow before it, which is LS2. So LS2 is the condition for B to extend, which is to make GP1 turns on. Now we'll take a look at GP2. The condition to make GP2 turn on, we look at the arrow before it, which is LS4. Okay, and finally, let's take a look at GP3. The condition to make GP3 turn on, which is to make B retract, is look at the arrow before it, which is LS1. So when LS1 is activated, GP3 will turn on to make B retract. So I'll write over here LS1. So this is how I fill in the blanks for this PLC ladder diagram based on the motion sequence, which I have already derived earlier. Okay, now we need to fill in the blanks for these solenoids. Okay, and as you can see from the earlier diagram, okay, let's take a look at the pneumatic drive circuit, okay, which I didn't copy and paste, okay, onto the previous page. Okay, so you can see that this is the pneumatic drive circuit. Okay, both are double solenoid. So to make A extend, okay, solenoid 1 must be energized. To make A retract, solenoid 2 must be energized. Okay, same goes for B. To make B extend, solenoid 3 must be energized. To make B retract is solenoid 4. Okay, so now we have the understanding of the pneumatic drive circuit. We know that they are double solenoid, so I do not need any latching circuit. So you can see, to make A extend, okay, I need to energize solenoid 1, which I actually label it over here for you. Okay, and to make B extend, I need to energize solenoid 3, okay, and so on and so forth. How do I know this? I already explained to you using the pneumatic drive circuit earlier on. So now, let's fill in the blanks for this. So you can see that, okay, I'm going to fill in the blanks. You can see that to make A extend, I need to energize solenoid 1. Which relay, okay, which software relay is the one that is going to make A extend? Okay, you can see over here, the answer is GP0, okay, which I've already labeled previously using this motion sequence diagram to help me. Okay, so I'll write here GP0. Okay, next, let's take a look at solenoid 3. Solenoid 3 is to make B extend. So which relay over here will make B extend? GP1. Okay, and next, solenoid 2 is to make A retract. So which relay over here will make A retract is GP2. And finally, solenoid 4 is to make B retract. So which relay over here is to make B to retract? The answer is GP3. So with this, we have already completed case study 1. I just want to emphasize to you again that it is extremely important, okay, to write your motion sequence diagram correctly and always label the software relays that is going to control the actions, okay, so that we can fill in the blanks very easily. So you can see that the motion sequence diagram plays a very big part in helping us to solve the PLC ladder diagram. Now, I will go through case study number 2. In case study 2, figure 7a and 7b shows the pneumatic control of the cylinder and the displacement step diagram. Okay, so we can see that this is the pneumatic drive circuit and this is the displacement step diagram. So we are supposed to write the motion sequence in abbreviated notation form, indicating clearly the limit switch for initiating each action. Okay, And the sequence of operations to be controlled by a PLC, design a program and ladder to achieve the desired control using the shift register technique. And again, you need a cold start PB to boot out the operation, and we will have a start PB to initiate a single cycle operation. So let's look further down, and again this is the PLC. You can see that all the input elements are wired to the input card, and all the output elements or the final control elements are wired to the output card of the PLC. We will now try to do the motion sequence in abbreviated notation for this case study too. And again, just like the previous example, I will copy and paste the displacement step diagram and the pneumatic drive circuit over here so that I do not need to keep scrolling up and down. So allow me to copy and paste the information. And I'm going to paste it here. Okay, so to begin drawing this motion sequence diagram in abbreviated notation, I will first indicate what is the button I need to press to start this motion sequence. Well, the question already told me previously I need to press the start PB. So when you press the start PB, what is going to happen? Well, look at the first step of this displacement step diagram. You can see that A will extend while B stays retracted. So the action that will happen is A extend. And how do you know A is fully extended? It will touch LS2. Now, let's take a look at the second step. Okay, you can see in the second step, A will stay extended while B will then start to extend. So the action we will see over here in the second step is B will extend. And how do you know B is fully extended? Well, it will touch LS4. And let's take a look at the third step. What happens? Well, you can see that it indicates a timing over here, and cylinder A and B stays extended. That means there is no action. So there's only a delay of 2 seconds. Since there's no action happening at the third step and there's only a delay of 2 seconds, so I will write over here a delay of 2 seconds. Okay. And look at the fourth step. We can see that there is some action happening, which is A will retract, okay, while B still stays extended. So now A will retract. Remember, I only write actions inside the boxes for the motion sequence diagram. So finally, how do I know that A is fully retracted? Well, you can see from the pneumatic drive circuit that it will touch LS1. And let's take a look at the final step. Okay, you can see that what happened is B will retract and A stays retracted. So the action that will happen is B will retract. How do we know that B is fully retracted? Well, look at the pneumatic drive circuit. It is touching LS3. And if you still remember what I told you for motion sequence diagram, we will always write the last condition, okay, and place it on the front as well. So let me write this in red, okay, so as to remind you to do this step always. And finally, what I'm going to do is I'm going to label, okay, all the groupings for this motion sequence diagram. Okay, so for instance, for A plus, which is first step, I will write over here GP0 because I will create a relay called GP0 to make A extend. And the same goes for the next step, which is GP1. So when GP1 relay is energized, software relay is energized, B will extend. GP2, okay, and GP3. So as I mentioned previously, the purpose of labeling this motion sequence diagram is to help me to solve the PLC ladder diagram easily. So with this, I've already completed the motion sequence diagram in abbreviated notation. And you can see that the difference between this case study and the previous case study is this step over here, okay, where nothing is happening, which means that the cylinder stays at its original position, which means that it stays extended for cylinder A, and it also stays extended for cylinder B. The only thing that changed is it needs to stay there for 2 seconds. So that's why I indicate over here, when it is at LS4, it will stay there for 2 seconds before the fourth step, which is A will retract. So that is the key difference between this case study and the previous case study. Okay, so for this figure over here, we are defining the global variable declaration table, which means that whatever things that has been wired to channel 1, we will give it a name. So for instance, the button that's being wired to channel 1, okay, in 00, okay, we call it start PB, and LS1 is being wired to in 01, so on and so forth. This is actually written based on this wiring diagram over here. Okay, you can see start button is being wired to channel 1 in 00, LS1 is being wired to channel 1 in 01. So you will learn more about this declaration, okay, in your lab. Now I will continue to focus on teaching you how to draw the PLC ladder diagram first. So again, just like the previous example, I will copy and paste my motion sequence diagram which I've written earlier, okay, and I will paste it over here so that I can actually solve the question easily. Okay, so now that I have done that, okay, let's proceed to solve this question. Okay, you can see that first I would like to label what is the purpose of all this GP. Okay, so you can see that GP0, GP0 was created to make A extend. So let me focus to write all these comments. So GP0, A will extend. And GP1 was created to make B extend. GP2 was created to make A retract. And finally, GP3 was created to make B retract. Okay, you can see that they have already helped us to fill in most of the blanks except for this. So let's take a look at GP2 now. So looking at GP2, okay, so what is the condition that starts GP2? We always look at the arrow before it, okay? So looking at the arrow before it, it is this timing, okay, 2-second timer. So what should I draw over here? It is the 2-second timer which triggers the GP2 control relay, okay, the software relay. So for timer, okay, when the time has reached 2 seconds, how do we know? Well, the output will tell me. You know that for timer, okay, just to recap, input, okay, is something that you trigger this timer. Preset time is the timing of this timer. Q is the output of this timer, okay. So when the time has reached 2 seconds, TR1.Q will turn on, okay. So I will fill in over here. The answer is TR1.Q. Because if you look at the motion sequence diagram, in order for GP2 to turn on, okay, the time must reach 2 seconds first. So when 2 seconds is up, GP2 will turn on. How do we know that 2 seconds is up? Well, the Q of the timer will tell me so. Okay, so when the time has reached 2 seconds, TR1.Q normally open will become closed and GP2 will then be activated. So we have already filled in everything on the shift register, okay, over here. now we will take a look at the timer itself. Okay, as we know, okay, this is a 2-second timer, so I will fill in the preset time first, T #2S. Who will start this timer? Okay, the timer as indicated on the motion sequence diagram is here, 2 seconds. So we look at the arrow before it, okay, which is LS4. So LS4, when it's being activated, will start this timer. So I'll fill in the blanks over here, LS4. When it's activated, it will become closed and the timer will start. So what should we fill in for Q? Okay, there's nothing for you to fill in here because Q is just the output of this timer and I already use the contact of this output timer. For elapsed time, okay, over here, it doesn't really serve any purpose, but in your lab, okay, you are expected to write a name for this elapsed time so that you can actually monitor the current time. Okay, elapsed time means current time. Okay, so in order to align to the lab, I will also give it a name for the elapsed time. You can call it any names you like. Okay, for me, I will just write elapsed time. Okay, or if you don't like, you can also do something simpler. Okay, you can just write display. Just call it any names you like. Okay, so in the lab, okay, when you're running the simulation software, you can actually see the real timing happening, okay, at this display here. So now that I've already filled in the timer, I want to take a look at this over here. So I would like to look at the pneumatic drive circuit of this cylinder first to confirm whether they are single or double solenoid. So as we can see from this pneumatic drive circuit over here, okay, both are double solenoid, okay, which means that I do not need any special latching circuit. And again, the concept is the same as the previous example. To make cylinder A extend, solenoid 1 must be energized. A retract, solenoid 2 will be energized. When B extends, solenoid 3 will be energized. When B retract, solenoid 4 will be energized. Okay, to make B retract. So let's take a look at this. To make A extend, okay, first I need to energize GP0, okay, which we already wrote here. To make B extend, okay, I need to energize GP1, which already written here. To make A retract, which is solenoid 2, I need to energize GP2. So I'll write over here GP2. And to make B retract, okay, I need to energize solenoid 4, which is using control relay GP3. So that when GP3 is activated, solenoid 4 will be energized and the B will then retract. So now we have already finished solving for this question. You can see that I depend heavily on my motion sequence diagram to derive this PLC ladder diagram. So it's important to get your motion sequence diagram correct from the start. Okay, now I'll take a look at case study number 3. We will now take a look at case study 3, whereby figure 9A and 9B show the pneumatic control circuit. Okay, so this is the pneumatic control circuit and this is the displacement step diagram. We are again expected to write the motion sequence in abbreviated notation. Okay, and we are going to implement this sequence of operation using a PLC. We have to design the program in ladder, LD stands for ladder, to achieve the desired control based on the shift register technique, okay, incorporating the following condition. A cold start PB is used to prime the operation or boot out the operation. A start PB is used to initiate a continuous cycle. You can see that in this particular case study, they mentioned continuous cycle. In the previous case study, we have been doing single cycle. Okay, then they also mentioned that the continuous cycle will come to a halt at the end of the cycle when you press the stop PB. Okay, so now with this, again, this is the PLC, okay, but all the inputs are being wired to the input card of the PLC, and all the final control and the output are being wired to the output card of the PLC. Just like the previous cases, I'm going to copy and paste the displacement step diagram and the pneumatic drive circuit over here. Okay, so I will first draw all these lines. And the question I already mentioned, I need to press the start PB to start the continuous cycle. So when they press the start PB, what happens in the first step is cylinder A will extend. And how do we know A is fully extended? It will touch LS2. And what happens in the second step? Well, A will stay extended while B extends. Okay, so the only action in second step is B extend. And how do we know B is fully extended? Looking at the cylinder B, it will touch LS4. Let's take a look at the third step. In the third step, A will retract while B stays extended. And how do we know that A is fully retracted? It will touch LS1. And finally, the last step. A will remain retracted while B will retract. So the action that we will see is B retract. And how do we know that B is fully retracted? Well, it will activate LS3. And again, just like what we have learned earlier, whatever is at the last condition, okay, will be put to the front as well. And also in this question, they say that it's a continuous cycle, so I need to draw the continuous cycle arrow. So what this means is this cycle will keep running and running until somebody press the stop PB. And just like in previous example, for when I'm doing motion sequence, I will always label. Okay, I'll write this GP0. So in the first step, okay, A will extend. And how do we make A extend? Well, we will energize a software relay called GP0. Okay, just a name that we have come up with in our earlier lessons. So I'll just write sequentially. So you can see that for A to extend, GP0 must be activated. Okay, and so on and so forth. So again, in the PLC software, you actually define I/O tag names as global variables, meaning that if you wire a start PB to in00, okay, I will call this variable name start PB. And this figure over here will tallies with this wiring diagram. Okay, as you can see over here. So start PB, okay, I call it start PB, it's just a name, okay. It's being connected to in00 as shown in the declaration table over here. Okay, so now I'll focus on how to solve this PLC ladder diagram. Just like in previous cases, I will copy and paste the motion sequence diagram onto this page so that I can solve the question easily. Okay. So you can see that this is the motion sequence diagram for this question. And over here in the ladder program, they created a relay, software relay called R20. Okay, actually the purpose of creating R20 in our example over here is to have the continuous cycle. Okay, R20 is just a name. You can call it any name you like, okay? But for standardization over here, R20 we always create to represent continuous cycle. Okay, so again, just want to remind you again, R20 is just a name. If you don't like R20, you can call it any name you like. Okay, you can call it R0, R1, R2, R3. Okay, so what is the condition to start this continuous cycle? As we have learned earlier, things that start we put on top of the latch, okay, and things that stop we put outside the latch. So according to a question, they already told me that you press the start PB to start the continuous cycle, and to stop this continuous cycle, you press the stop PB. Okay, I just want to show you where exactly it is stated in the question. So let's take a look at this. It actually states here, when you press the start PB, you'll start the continuous cycle. It will stop when you press the stop PB. Okay, and again, just like in previous cases, I will label what's the purpose of all this control relay. So we can see that GP0 was created to make A extend. So I'll write here, A extend. GP1 was created to make B extend. GP2 was created to make A retract. And finally, GP3 was created to make B retract. Okay, so let's focus on how to fill in the blanks for this shift register. Okay, so you can see that the conditions to make GP0 turn on, which is A extend, we look at the arrow before it, which is the start and the LS3. So over here, when you press start, R20 will turn on. So we will use R20 instead, okay, to turn on GP0. So as you know, when you press start, R20 will turn on, so the contact will also close. So which means that the continuous cycle has just started. And it is one of the conditions to make A extend. As for the rest, they already fill in for us, okay, as you can see over here. So now, let's take a look at the solenoids. Okay, so you can see over here, for the solenoids, there are only 3 solenoids. Okay, let me double confirm with the pneumatic drive circuit. Why are there only 3 solenoids? Okay, as you can see over here, well, cylinder A is using a double solenoid directional control valve, and cylinder B is using a single solenoid directional control valve. And we know that single solenoid we need special latching circuit. Okay, because to make B extend, solenoid 3 must be continuously energized. And to make solenoid 3 continuously energized, we need a latch. Okay, so let's go back to this question, this problem again. So we know that to make A extend, solenoid 1 must be energized, which is GP0. To make B extend, solenoid 3 must be energized. Okay, I'm supposed to fill in the blank. And to make A retract, solenoid 2 must be energized, which is controlled by GP2. As you can see, you're supposed to make A retract. So for this particular line, solenoid 3, okay, to make B extend, first GP1 must be energized, okay, and it will stay there until it's time to retract, which is GP3. Okay, so in order to make B extend, which means that I need to constantly energize solenoid 3, I will create a special latching circuit over here, whereby the purpose of GP4 is to make B extend and retract. Okay, so I'll fill in GP4 over here first. So who will make B extend? Okay, so when GP4 is energized, okay, the contact here will close and solenoid 3 will be energized, and it will stay there because of this latching circuit. So I will say that GP1, okay, as I can see over at my motion sequence diagram over here, GP1 will make B extend. So GP1 is the condition to make B extend, which means that I need to energize GP4. So when GP1 is being activated, GP4 will turn on and solenoid 3 will be on to make B extend. So when will B retract? Well, B will retract when GP3 is being activated. So to make the cylinder retract, I just need to off GP4 because GP4 is controlling the solenoid 3. So over here, I will just fill in GP3. Because as you can see from my motion sequence diagram, GP1 will make B extend. So GP1, things that make B extend I'll put here, okay? And GP3 will make B retract. Because when GP3 is activated, this contact will open and GP4 will be off and solenoid 3 will have no more power. The cylinder will just retract. So what's the difference between this case study and the previous case study? Well, as I know, first, I learned about continuous cycle again. Okay, so I draw a relay to represent continuous cycle and I call it R20. Next, I learned about single solenoid directional control valve. They need a special latching circuit as I have seen over here. Okay, and in order to control this single solenoid to make B extend, okay, GP1 must be activated in this example here and it will stay on, okay, because GP4 has a latch. So hence the cylinder B will stay on because solenoid 3 will be constantly energized until it's time to off it because I want B to retract. So to off it, GP3 must be activated, okay, which is shown here in the motion sequence diagram as well. And then solenoid 3 will be off and the cylinder will retract. So these are the key learning points you have learned so far for this example. So some students may start to ask, how am I going to remember all these steps? Well, first you have to do it very systematically. Look at the question and see whether is it a continuous cycle or single cycle. If it's a single cycle, we will do it just like the previous two examples, whereby we don't have any continuous cycle relay because it's just a single cycle. And also, to implement such sequential control, okay, I will then draw the shift register technique, which we are expected to know how to derive this template out. Okay, if you have forgotten, again, look at the video, which I've taught you how to derive this shift register. And finally, look at whether you have timer or counter, which in this case I have none. And if there's none, you just proceed to draw the output, okay, as we can see over here. So you draw what controls the final control element or the output elements. So these are the key steps to solve the PLC ladder diagram. Now I'll go on to the last case study for PLC 3, which is case study number 4. So in case study 4, we take a look at the pneumatic drive circuit, okay, and the displacement state diagram. So this pneumatic drive circuit is actually the same as case study 3, and for the displacement state diagram, the difference is this timing over here. Okay, so again, we are expected to write the motion sequence diagram in abbreviated notation. And we are also supposed to implement the sequence operation using a PLC ladder diagram. Okay, so these are the conditions. First, you must press the cold start PB to boot up the operation, okay, which is to prime the operation. A start PB is used to initiate a continuous cycle. The continuous cycle will come to a halt when a stop PB is actuated or when the counter tracks the number of operating cycle, which register a count value of 10. When the preset count is reached, the counter will reset automatically. So what's the difference between these case study and the previous one? Well, the previous one do not have a counter. In this example, we have a counter, which I'm going to revise with you what is a counter later on. So again, this is the PLC wiring diagram, same as previous. And now we will take a look at this motion sequence in abbreviated notation. So just like the previous case study, I'm going to copy and paste the pneumatic drive circuit and the displacement step diagram so that I can do this abbreviated notation easily. And just like previous case, I will write the lines, and you need to press the start PB to start the cycle. Okay, so what happened in the first step? Well, A will extend. And how do we know it's fully extended? It will reach LS2 as shown in this pneumatic drive circuit. Second step, okay, the only action that happened is B will extend. And when B is fully extended, it will touch LS4. Third step, we can see that there is no action from the cylinder. The cylinder A will remain extended, cylinder B will also remain extended, but there's a delay of 2 seconds. So I'm supposed to write this delay over here on the motion sequence diagram. And just like case study 2, I'll just write 2 seconds here, or you can write wait 2 seconds, up to you. So let me write this nicely. So you can write wait 2 seconds, or you can just write 2 seconds here. And fourth step, A will retract while B stays extended. Okay, and then how do we know A is retracted? Okay, it will touch LS1. And lastly, you will see that A, nothing happens, and B will be retracted. And how do we know it's fully retracted? Well, it will touch LS3. And again, just like previous, okay, since this is a continuous cycle, okay, I'll draw this arrow and also bring the last condition to the first. And finally, I would like to label all this GP0, GP1, GP2, and GP3. The purpose of writing all this is to help me to solve the PLC ladder diagram later on. Okay, so that I create this relay to control the cylinder action. And this is again the I/O tag names, okay, for the global variables, which I've explained to you earlier on. And now we will solve this PLC program in ladder. So just like in previous cases, I'm going to copy and paste my motion sequence diagram over here so that I can actually refer to them easily. Okay, so let me first label my ladder diagram. As I have told you earlier, these are the key steps to draw the ladder diagram, okay, especially for sequential code. First is you check whether the ladder diagram or the questions need continuous cycle. In this case, they need, okay. So this is R20 represents continuous cycle. I told you that we will use standard naming convention, okay. R20 is just to represent continuous cycle in our context, okay. So when you press start PB, R20 will turn on, the cycle will remain on because there's a latch. And when you press stop PB, R20 will be off. And what's the purpose of GP0? Okay, we can see from the motion sequence diagram is to make A extend. Okay, same for GP1, B extend, GP2, A retract, and GP3, B retract. Okay, how do I know all this? Well, I just need to look at the motion sequence diagram. GP1 to make B extend, GP2 to make A retract, GP3 to make B retract. So this thing over here we know is a shift register. So just remember that after drawing continuous cycle, okay, if there is, okay, draw the shift register technique. And I just noticed that we have a blank over here to fill in. So let's take a look at GP2 in the motion sequence diagram. So if you take a look at GP2, what is the condition that triggers GP2? We look at the arrow before it, which is this timing of 2 seconds. So just like the earlier case study, okay, which is case study number 2, since 2 seconds is up, then you will trigger GP2. So I'll write this here as TR1.Q, so that when the 2-second timer is up, the contact will close and GP2 will turn on, which is what this motion sequence diagram is showing. When 2 seconds is up, GP2 will turn on. So how do we know 2 seconds is up? We will use the contact of the timer, which is a normally open contact, TR1.Q. .Q represents the output of this timer. So when 2 seconds is up, this contact will close and GP2 will turn on. Okay, now we will fill in the blanks for the timer. Again, focus on the timer, on the motion sequence diagram, which is the 2 seconds. So first I'll write the preset time, T#2S. And then I will see who triggers this timer. Okay, well, look at the arrow before it. It is actually LS4. So when LS4 is activated, okay, you will start the timer, which is what is happening in this case. And as I've told you earlier, Q, you do not need to write anything here because I already used the output of the timer as a normally open contact. And for elapsed time, okay, you can just write a name. I will call it display 1. And what happens is when you do this PLC program in the lab, okay, you can actually see the software showing you what is the elapsed time, okay, using this name. Okay, and they have also drawn the latching circuit for me, which is GP4, okay, which I've done previously. GP4 previously, as in previous case, GP4 is a special latching circuit, as you can see over here, and it is used to control solenoid 3. Well, because this is a single solenoid directional control valve, it needs such a latching circuit. So as you can see from the motion sequence diagram, when GP1 turns on, B will extend. When GP1 turns on, okay, where the contact close, GP4 will turn on and the contact will close. Solenoid 3 will turn on, which make B extend. So I will just summarize over here. When GP4 is on, okay, B will extend because solenoid 3 is energized. When GP4 is off, okay, which means that when GP3 is activated, normally close become open, okay, GP4 is off, B will retract because there's no more power to the solenoid. It will go back to the spring position to make it retract. Okay, so now I'm only left with the counter to fill in. So the question says that the counter is supposed to count the operating cycle, okay? So let's take a look at the question first again. I'm supposed to count up to 10, okay? And when the preset count is reached, the counter will reset automatically. Okay, so I'm supposed to count the operating cycle. Looking at the motion sequence diagram, how am I going to implement counting on the operating cycle? Well, some students will say, okay, can I use GP3 as the input to this counter? In other words, when GP3 is activated, the counter will just register a count once. Well, it sounds logical. Well, because when this sequence is being activated, okay, what happens is when GP3 is on, okay, you want to count that as a complete 1 cycle. Okay, that's what most students will propose, okay, which is using GP3 over here to trigger the counter, to calculate the operating cycle. However, we cannot use GP3. Why is that so? Take a look at this ladder diagram over here. Call start PB is being wired to GP3 right at the start. So what happened is, when you are actually giving it a cold start, or you're actually priming the operation, when you press cold start PB, GP3 will turn on, and even though you have not officially started the cycle, you already count once. So I cannot use GP3 as the input to the counter, because when you press the cold start PB, GP3 will turn on and the counter will register a count of 1. Okay, even though you have not pressed the real start button. So the next best answer is to use GP2. Why? Because GP2 is like the sequence has already completed 3/4, okay, of this entire cycle. So when GP2 is activated, I will say that the cycle is almost going to complete and I can register a count of 1. Okay, that's the rationale of why we use GP2 as the input to the counter. Okay, let's fill in easy things first. What is the preset count? I already showed you that it's 10. And finally, how do I reset this counter? Well, the question says, when the preset count is reached, you will automatically reset the counter. So I will actually write over here, CTR1.Q. Okay, because when the preset count is reached, CTR1.Q will be activated and the counter will be off. So do I need to wire anything to the Q? Well, actually don't need, because Q is just the output and I'm already using it to reset the counter. Finally, do I need to have another name to the count value, current value? It's best to write a name so that in the lab, okay, when you're doing the PLC programming, you can actually monitor how many counts, okay, what is the current count. So I'll call this display 2, okay. You cannot call this display 1 again. Why? Because display 1 is already being used for elapsed time, so I call this display 2. Of course, you can call it any name you like. And lastly, let me check whether I have already completed this question. Okay, let's read the question again. The question says, the continuous cycle will come to a halt when the stop PB is actuated, which is already drawn. The count value, okay, reach 10. Okay, so I'm supposed to use the counter to stop the continuous cycle as well. So R20 is my continuous cycle. There are two stop conditions. One is the stop PB, another is the count value. So how do you know that the counter has reached 10? Well, the output of the counter will tell me. So I will draw a normally closed CTR1.Q so that when it reaches the count of 10, normally closed will become open and R20 will be off. The whole cycle will stop. So with this, I've already completed this question. So in this chapter, we have revised on the timer. We have also revised on the counter. We have learned about the shift register technique, okay? And then we know how to implement the shift register technique to solve sequential control. We also recall how to draw latching circuit for single solenoid directional control valve. So when you're solving this PLC programming ladder, it's very important to do things systematically. Always draw the continuous cycle first if there is. After that, draw the shift register technique. After that, draw the timer or the counter if there is. And finally, draw all the outputs. Okay, so you must be very systematic when it comes to drawing this PLC ladder diagram for this sequential control. So we have come to the end of PLC 3